Loose lens retinoscopy. This is one of the harder skills to learn in ophthalmology, both for you and really for me. When I was a resident doing my surgical training, it probably took a good 2 years before I really got any comfort, and I'm still getting comfortable with it. You get better with time. I thought this would be an interesting topic and a useful one because this is something you can actually use in your office. Now, I guess retinoscopy is part of your COMT certification. COT? Is it really? Okay. Do they have you do it using the manifest, the phoropter? Okay. The phoropter is a useful way. Personally, I think the loose lens retinoscopy is more useful. And the reason why is who are the patients who need retinoscopy? It's often children. And then like we already showed you often can't get a child up to the phoropter. And if you can do loose lens retinoscopy, you can do retinoscopy on anyone. And so I thought this is more useful. I personally don't have a retinoscopy through a phoropter. I guess I could figure it out, but I found this way a little bit easier. The difficulty with retinoscopy in general is that it is hard to teach because, one, when people describe things to you, it's very hard to visualize, especially if you've never seen it before. You get absolutely no feedback, at least with a phoropter manifesting people. They can say, I can see one better than two. You know, with this, you get nothing. All you're looking at is the reflex in the back of the eye, and by holding different lenses in front, trying to estimate what we think the glasses prescription is based on this. So it's challenging. So here's the theory on how retinoscopy works. If you shoot a light from your instrument into the eye, and it's coming straight in, if that eye is in perfect focus, they're not nearsighted and not farsighted, they've got perfect vision, as you move your light up and down, the reflection should hit a single point on the retina, bounce back to you, and you should have a nice bright red reflex from that. Now let's say you take an eye someone's a little farsighted. Well, light coming into their eye doesn't focus right, it actually focuses behind the eye. And if you move your retinoscope up and down, the light moves up and down, and where it strikes the back of the retina, it also moves up and down in synchrony with you. When it comes back at you and you look at it, you're seeing a with reflex because the reflection is moving the same direction you're moving your instrument. If we hold a lens in front of it, not quite strong enough yet, we don't have the correct prescription, you still see a with reflection. The light beam going up and down, the reflection on the back of that retina is also moving up and down. We add a stronger lens, the correct prescription in this case, and you hit that retina perfectly, the light bounces back at you, you have a nice bright reflex, you've neutralized the reflex, this is the correct prescription for this eye. Now if we decide to use too powerful lens, we put a very strong plus lens in front of that eye, the light actually focuses in the middle of the eye. And as you move your light, you almost get a seesaw reaction, and the reflection off the retina is actually in the opposite direction you're moving. We call this the against direction. So with versus against. Now what does that look like in real life? Well, before we go to real life, let's look at a cartoon. This is a light beam, and your retinoscope produces a beam of light. I like to make mine nice and thin, and you can move it across the surface of the eye, up, down, left, and right, it doesn't matter. But when we look at that reflection off the retina, it moves in the same direction as you can see here. It's kind of a yellowish, orange, red color. So let's do the same experiment. We'll add a plus lens and see if we can figure out the right prescription. So let's add a +1 to the system, and we still have with motion. So it doesn't look like this lens is powerful enough. Things are still focusing behind the eye. Okay, well, let's get rid of this +1 and put something a little bit stronger. We'll try a +2. Now when we do a +2, the reflection is still with, it's still moving the same direction at your light beam as it plays across the surface of the eye, but you can see that the reflection has actually gotten a little bit wider back there. That's a good sign. When it gets wider like that, you're getting closer to the right prescription. Let's try +3. This is perfect. This is the right prescription to get this eye in focus. A +3 is what did it. So we've got it right on, perfectly focused on the retina. Let's go a little bit further, see what happens. +4, we're too strong now, and you can see the reflection is actually moving against us, and so that's not what we want. So that's how you do basic retinoscopy. And don't worry, I've written these steps down in your notes, and we're going to do a bunch of models ad nauseum until we figure this out. There are 3 steps to retinoscopy. The first step is you have to start with motion. If you have an eye that has against motion right at the beginning, you're going to become confused. You have to have with. The second step, you add power, like we just did, until you neutralize the reflex. And finally, at the very end, you subtract a working distance, and we'll go over that in a second. So this is a cardboard cutout I created just for this lecture to try to simulate what this looks like. I could have animated everything like that last little animation, but it was just going to take forever. So basically I used South Park techniques, cardboard cutout, and we're going to see if we can use this to figure it out. So once again, we started with width. The reflection is going with us. We add power to the system. Still not strong enough. I'm doing it in a couple of different axes, and I'll explain that later. But for now, we're just looking for spherical problems. Let's try a +3. Our beam's getting wider. We're getting closer. We're almost there. So +3 is not quite that. Let's try a +4, see what happens. And +4, pretty darn close. Hard for me to estimate that perfect reflection using cardboard, but this is close. And I think we'll try a +5 just to see what happens. Let's try it. Is this too strong or not? It is, because we have against motion. And that's basically how you do retinoscopy. Not bad, not bad. Let's move on. So, we ended up with a +4, got this eye in perfect focus. However, the last step, as you remember, is there is a working distance. You have to subtract -1.5 from your final spherical answer to come up with the correct one. And here's why. This is the working distance. What's that all about? Well, so far we've assumed that when light is coming into the eye, it's coming in straight from, let's say, infinity or across the room, really far away, before it focuses on the retina. But the reality is we don't sit that far away. We sit about 66 centimeters or 2/3 of a meter, about an arm length away. Light is actually diverging a little bit before it hits the eye. And so you have to do a correction for that. And most people, this is sort of a computer reading distance, that correction is about a +150. So we subtract that from our end result to go with the answer. Now, you don't have to worry about the theory. Just realize that at the very end you have to subtract a working distance. So let's do another example. Once again, we have to start with motion. So everything's with. This is good. Let's try the other axis just to make sure everything's okay. Good. Step 1 is complete. We have width, so we can continue by adding power. Step 2, add power until you get rid of that. So we're adding power. It's getting a little bit thicker back there, a wider reflex. This is a good sign. And in every direction, good. Let's add a little bit more power, see if we got it. A +2. And, yep, looks like we pretty much have it. All right. Let's try the other axis, make sure it's okay in that way. No astigmatism. So it looks like a +2 is probably the right lens. Let's try a +3 just to see if we can get a little bit more. And we have against, so we've gone too far. You never want against. Against is bad when it comes to retinoscopy. So we know that our answer here is what? A +2. Correct. So we'll get our lenses out, +2. And what I like to do whenever I have this situation is I don't put the lens back into the box, I put it on the counter. Because otherwise you'll forget. And you do not want to be doing memorization while you're trying to do this technique. It takes enough effort to just do it. And so put it aside. And so our final answer here is a +2 sphere. But remember, the last step of retinoscopy is you have to subtract your working distance. And our final answer is this is a +1/2 diopter hyperope. All right, another example. Step 1, start with width. Good. Nice and width. All right, we're going to speed up a little bit. That's pretty good. Let's add some power. Step 2, start adding power to neutralize a reflex. It looks like we may have hit it. So let's try it. Looks pretty good. And let's set aside our lens. We don't want to lose it. And let's try adding a little bit more power, see if that helps. We add more power. Nope, we've got against motion. Let's check the other axis, make sure it's still against. It's against. And so we know that our answer here is a +1 sphere. Or at least that's what the lens that gets us in focused. So we end up with a +1. But remember, the final step, step 3, is always subtract a working distance. And you end up with a -50 sphere. Not too bad. All right. We got against motion. Uh-oh, what do we do now? Well, remember, step 1 is you have to start with motion. If you have against right from the offset, you're in trouble. So what do? You back off. Start with a -2, or -4, or -10, or whatever it takes to start with motion. If you don't start with width, you'll become very confused. So we went back to a -2. Good. Now we can add power. We'll go to a -1. That's a diopter stronger. And it looks like we've hit the perfect prescription here. I think we're good. And so let's try the other axis, make sure it's in both ways. Everything looks fine. And so it looks like our answer here is a -1. And so once we do our correction, it's a -1. Subtract your working distance. Always do that at the end. Don't try to do it in your head while you're doing it. Do it at the end. And our answer is a -250 sphere. Okay, another one. We got against. It's really against. So we can't start with against. We had to have width. You'll just get confused. Step 1, you had to have width motion. So let's throw a -2. We still have against. This is no good. If you start here, you become confused. Optometrists, they start with negatives. They do everything different, but in ophthalmology, at least, this is how we do it. So let's throw a -4. Okay, finally, we have with motion. We can continue. Let's try the other axis. We can continue. Good. Now, and only now, can we start adding plus. So we go -3. It's a diopter stronger. And it looks like we've hit probably the perfect prescription here. Let's check the other axis, make sure it's both ways. This patient doesn't have too much astigmatism. Nope. All right, set your lens aside or leave it out, because if you put it back, you'll forget, you'll do the math in your head, you'll mess it up. And so what we have here is a -3 sphere, got this eye in focus, you correct for your working distance, it's always a -150, and you end up with a -450 spherical power. So that's how you do basic retinoscopy. And so, what are the 3 steps? I'm going to hit you again with it. The 3 steps are you have to start with width, then you add power to neutralize the reflex, and at the very end, subtract the working distance to come up with your final prescription. So what about astigmatism? Now this has been pretty easy so far. If it was this easy, anyone could do it. It's not an issue. Let's look at another eye. Step 1, start with width. Good. We can proceed to step 2. Let's start adding some power. We'll add a +1. Okay, we're still with, not quite there yet. Let's check the other axis, not quite there yet. We're getting there. Let's add another diopter of power. All right, +2. Let's try this. It looks like we maybe have hit it here. In fact, I think we have. Okay, let's check the other axis. Uh-oh, we still need some more power this direction. Don't worry about axes. Is it 90? Is it 180? Just keep your instrument in the same position. Set that lens aside and keep going. Set it aside. Keep going. Start adding power, and we'll continue moving our beam left and right until we get it. Boom, we've got it. And so these are our 2 lenses. Now, don't try to do the math in your head while you're doing this. Here is how I calculate the prescription based off this. The sphere is +2. The cylinder power is the difference between them, so it's a +2 +1. It's just like using a lensometer, right? You start at one number and the amount you shift it is your cylinder power. Same thing with this. So this is a +2 +1, and the axis is at 90. And we know it's at 90 because our light beam is going up and down. And if you're not sure, hold your light beam up to the phoropter and look at the little angular degrees on there and make sure it's lined up with 90. And that's how I remember it. I don't try to think I was moving left and right, but the axis is always 90 degrees off the power. It'll confuse you. Just put these lenses aside and at the very end look at it. This is a +2 +1 at 90. So we write it out. A +2 +1 at 90. But remember, there's one last step, and that is to subtract your working distance. And you subtract it from the sphere, and that's all. You don't need to subtract it from your cylinder power. So the final answer here is a +50 +1 at 90, and that's the prescription. Let's do another example. All right, step 1, always start with width. You have to start with width or you'll become confused. All right, so we've got width motion in both directions. Let's start adding power. Still have width, so not enough yet that direction. Let's try this direction. No, still need more. Let's add some more power. Try +2. All right, we're getting close. Our beam is getting a little wider. We're nowhere near in this direction though, so let's keep adding power until we neutralize these things one at a time. So let's try this way. No, still need a lot more this way. However, this way, we've got it. This is the right prescription in this direction. Let's set this lens aside. Set it aside or you'll forget. Just set it aside. Keep adding power and let's go back to the other direction until we fix that too. Still have width, not quite there yet. Let's try this +5 lens. Perfect. Now we have the right power for that meridian. Set the lenses aside, and now you can start thinking about the numbers and writing these things down. So this prescription is what? It's a +3 +2. It's the difference between them. And the axis, we can just look at where our light beam is oriented right now. It's going sort of horizontal. We know the axis is at 180. So the answer is a +3 +2 at 180. Write it down. Don't do the math in your head. Just write that down. And at the very end, subtract your working distance, and our final prescription is a +150 +2 at 180. Not too bad. Let's do another example. This is good practice. All right, we've got against motion. We can't start with against motion. You're going to get confused. So what do we have to do? We need to back off because you've got to start with width before you can figure these things out. So let's put a -2 up. Good. We've got width motion that way. We still have against. This is no good. You cannot have against motion at the beginning. You'll get confused. So let's throw a -4. If I got to go to -10, so be it. Now we have width motion in that direction. We have width motion in this direction. Now we can continue and add power until we neutralize it. So let's add a diopter, -3. We still have width, not quite there yet. Let's check the other direction. We've got it. We've got it this direction. Let's set this lens aside. Set it aside, you'll get confused. Just set it aside, get a stronger lens, and keep going the other direction. So we're going to add a little power. No, still need a lot more, it looks like. That's surprising. Okay, let's add some more power. -1, let's try that. I think we may have it. This might be it. Do I try it for more? Do I dare? Let's try plano. No, plano's too strong. The -1 was the right one. So put these lenses aside. Put them aside. If you don't put them aside, you'll get confused. Now you can write it down. This is a -3. The difference is a +2, and the axis is at 90. You write this down, -3 +2 at 90. Then you do the math. Subtract your working distance, and the final answer is a -450 +2 at 90. Not too bad. All right, we're going to do this one more time. We have against motion here. It's no good. Can't start with against. You got to have with. You can't continue. No, still a problem. It's okay this direction, but it doesn't matter. You got to start with with in every direction, otherwise you'll become confused. So let's throw a -4. All right, we definitely have with this, so this is good. Let's try the other axis, make sure it's still good. Now we have with in all meridians. We can continue with step 2, which is where we add power to neutralize the reflex. Try a -3. I think we've got it. We've got it this direction. So let's set this lens aside before we get confused, and now we'll continue to add power and work on the other direction. So we'll try a -2. No, not quite there yet. We're getting closer though. I think we're getting closer. Let's try -1. I think we've got it. I think this is it. Set it aside, then write things down. This is a -3 +2, that's the difference between them, and the axis is at 180. Write that down, -3 +2 at 180. Then, and only then, do you subtract your working distance from that sphere power, and your final answer is a -450 +2. All right, we're going to do this one more time, and then we'll continue on. I know I'm beating this into you, so I'm sorry. Start with against. This is no good. You can't have against motion. You got to have with. Still have against. This is no good. We can't have this. We got to have with motion. -4. Finally we have with motion. Let's make sure it's in both axes. Good. We have with in both axes. Only now can we continue. Let's start adding some power. Step 2. We'll add a -3. Oh, not quite there yet. Let's try the other way. Perfect. We've got it this way. What do we do with our lens? We set it aside. So I'm going to put this on the counter. Go get a more strong lens, and we'll work on that other direction. Still have width. Might need a bit more. Let's get a stronger one. -1. Still have width. You know, it actually looks like I might need a whole bunch more looking at my reflection here. So let's add more. Plano. That's a diopter stronger than -1. No, not quite there yet. +1. I think we're getting closer. We may have it. This person has a ton of astigmatism. +2. Let's try it. I think we got it. This looks like it's our answer. I'm getting greedy now. We're going to try a +3. We've gone too far, so the answer was a +2. So you set these aside. Perfect. And what is our answer here? It's a -3 +5. And our axis, as you can see where my light beam is oriented right now, is at 180. So you write it down, and only then do you do the math, subtract your working distance, -450 +5 at 180. All right, 3 steps to retinoscopy. Remember these? I know you do, because we just said them like 5 million times. You got to start with width. Then you add the power, and at the very end you subtract. But let's do astigmatism, because all that stuff, well, we've been doing astigmatism. I take that back. Let's do against the rule stuff. Technically, we've been doing a rule astigmatism, either against the rule or with the rule. Let's do unrule, something in between. We haven't really been doing angles yet. And what does that look like? Well, here we go. All right. We've got, uh-oh, what is this? Our reflection is at a funny angle, isn't it? That's odd. So what do? You just rotate your beam so that you're in sync with that angle, and then you continue doing your steps just like before. You got to start with width. All right, I've got width in that direction. This is good. Do I have width this? No, I'm still against. This is no good. We had to start with width. You have to start with width. You'll get confused. Let's try -4. Perfect. We've got width motion that way. We've got width motion that way. Now we continue with our standard retinoscopy technique. Step 2, we start adding power. So we'll add a diopter. Let's see if we got it. Nope, not quite there. We may be close the other direction. Let's try. Perfect, we got it. We've got the prescription that way. Let's take that lens, set it aside. You'll get confused otherwise. Just set it aside. Keep adding power until you get the other direction. All right, we're getting close. Not quite there yet. Let's add another diopter. I think this is it. This looks like it. All right. Set the lenses aside. Yes?
So if on your first pass you see it had an oblique, you're not going to go with horizontal and vertical. You're going to stick with the obliques.
Yep. I try to get it so that the reflection looks exactly in the direction that I'm moving. And it's hard to figure out sometimes, especially if it's a funny angle or it's a funny reflex, but you do your best. And as far as figuring out this prescription, it's all the same steps. Once again, we set our lenses aside, we look at it, this is a -3, +2, and you look at your axis, and if it's not obvious, you hold it in front of your phoropter and look at the angles on that thing. I'm going to estimate this is about a 90, 120, and so what do we end up with? We end up with a -3 +2 at 120. Last step, you got to subtract your working distance, and you end up with this prescription, a -450 +2 at 120. All right, so, yes?
I sometimes get confused when I get that scissoring.
Yes. Well, we've been assuming that the eye is a perfectly spherical structure, and the lens is perfectly spherical, and it focuses at a single point. But the reality is the eye has a fair amount of aberrations. The cornea is not perfectly spherical. It has a slope out at the edge, and that slope can cause some distortion. The lens is actually steeper in the middle. It's the opposite, and so these spherical aberrations can cause issues. Plus, if they have a cataract, the center of the cataract may be stronger than the outside of the cataract, and you may have a different movement of the light in the center compared to the outside, so it's going in different directions, and it gets very, very confusing. The key is just to look at where the light is right in the middle of the pupil as best you can, and you do your best. That's all you can do. And sometimes you just don't get it, but you try. But, in summary, 3 steps. Start with width, add the power, then you subtract. And now we're going to test ourselves with a couple of cases. These will go fast. This is the speed at which I retinoscopy, and we'll see if we can figure it. And we're going to do everything in our head. I'll talk out loud just to keep us from getting bored, but we're going to do everything in our head. So here we go. Start with width. Good that direction. Good that direction. Okay. Let's add some power. +1. Not quite there yet. Not quite there yet. Let's add some more power. +2. Okay, that's our 150. Okay, we're getting there. Oh, I think we've got it. I think we've got it. Let's put this lens aside and continue on in the other direction. Let's try +2. No, not there yet. +3. I think we got it. This is the prescription. Now if we do this in our head, this is a, let's try 4. I'm getting greedy. Sorry. No, too far. I'm glad I set that first lens aside, otherwise I would have lost it and forgotten. So what's our prescription? It's a +150, +150 at 180. In our head, we do the subtraction, and it comes out to being a plano +150 at 180. And let's see if we are correct. Plano +150 at 180. That's how we do it. Let's do a harder one. All right. Well, I think we got it right off the bat. Good. So that's a plano that direction. Oh, we still need some more power that way. So let's add a +1. No, not quite there yet. Let's add another one. We're getting closer. Our reflection's getting larger. Let's add another one. I think we've got it. Perfect. Am I getting greedy? I am getting greedy. Let's try it. No, we've gone too far. So let's get that +3 lens out, lay it on the counter before I forget, and our answer is it's a plano +3 at 90, and we do the math in our head, and the final answer is a -150 +3 at 90. Let's see if we've got it. Perfect. -150, 390. One last one. This is our last one, I promise. It's a funny angle. Got to change. All right, good. We've got with motion in this direction. That's fine. We've got against. No, that's no good. We can't have against. You got to start with, or you're going to get confused. Let's throw a -2. Perfect. We've got with motion that way. We've got with motion that way. We can continue. Let's add some more power to the system. Not quite there yet. This direction. We've got it this way. Let's set our lens aside. We're going to get confused and keep going the other way. Plano. No, not quite there yet. +1. Oh, they've got a fair amount of astigmatism. Not quite there yet. +2. Let's try it. Oh, no. Man, this is a high astigmatism. Let's try another one. Okay, we're getting close. I can tell. Let's add another one. Boom, we've got it. So, set our lenses aside, do the math in our head. This is a -1 +5 total. And the axis is about 45 degrees. You do the math in your head, and it ends up being a -250 +5 with an axis of 45 is our final answer. -250 +5 at 45. I have put this sample in your notes so that you can kind of figure out how this works. The same photo from this last one is in there, so it should make sense. But in summary, there are 3 steps to retinoscopy. You have to start with width, then you can add power to neutralize the reflex, and you may have to do it in different meridians and set your lenses aside. And the last step is you subtract your working distance at the end. Thank you.